Right, in this question we have two equations that have created an area, right? And in both parts they're going to ask us to rotate this area around both the axes, right? And we want to find the volume of the shaded portion, right, as it's rotated around either of the two axes. So we're going to start with the x-axis. So I've drawn in more detail what this will look like as you rotate it around the x-axis. So we're going to have an outer volume, and then we're going to have an inner volume that we need to consider. So the easiest way to think about this is if we take the volume of the entire thing underneath the graph y equal to square root 4 minus x, and we take away that inner volume which looks like a cone, it'll give the volume of the solid that we're after. Okay, so let's get into it. So the first thing we need to do is we are about to consider these two functions, and we need to make sure we have equations that are relevant. Okay, so we're rotating around the x-axis, so we need a function that's y equal to, because we need y squared at some point. So I'm going to take both my equations and I'm going to change them into y equal to format. That's just going to make it easier for myself when I get to the integrals. Okay, so we can see that we have one of the graphs is already y equal to square root 4 minus x. That's great. And the other one is x plus 2y equal to 4. I'm going to just change that into y equal to something. That's going to be y equal to 4 minus 2. Sorry, not 4 minus 2. 4 minus x divide by 2, right? Now later on we're going to probably have to anti-differentiate this. So I'm just going to tidy things up, and I'm going to make this y equal to 2 minus x over 2 in preparation for when we need to integrate. Okay, so let's set our integrals. Okay, so we're going to state we want to find the volume. Right now we don't want to find the volume of that entire thing, we want to find the outer portion. All right, so we're going to take the volume of the entire, right, solid, right, which will be defined by the topmost line, right? That's the y equal to square root x minus 4. If you think back to when we were doing areas, right, if we wanted to find the area between two lines, we took the volume of the upper line and we subtracted the volume underneath the lower line. That gave us the volume between, or the area between the two. We're doing exactly the same thing here except with volume. The only difference is we have to be careful with the way we write our integrals. Okay, so the boundaries are from the x equal to 0 to x equal to 4 as shown on the graph, and we have pi, right? I'm going to write the volume formula here off to the side just so that we can keep track of what we're adding in. Okay, so we have pi. We need y squared for the top line, right? Y squared will just be this equation here squared, right? And when I square that equation, all that's going to happen is I'm going to get 4 minus x, okay, with respect to x, right? Except that's now the volume of that entire solid, right? In other words, if I had to shade the entire region underneath this graph, that is what this will give me. But I don't want that. I want to take away, right? I want to take away the volume of that cone. Okay. Now looking at this, right, I have two ways that I could do this. The first way is I could set the integrals based on the straight line graph. Alternatively, this is just a triangle. Okay, so we could also work out the volume using the volume of a cone, right? But now to go and write the volume of the cone and substitute in the values it's just easier to set the integral and do it like this. Okay, so the integral boundaries are the same. Okay, we want y squared. This is y in this case. So in other words, I want 2 minus x over 2 squared, right? And this is with respect to x. Okay, now before you go and expand that bracket out and collect like terms, remember we know how to anti-differentiate this. Remember, this is a linear function, right? It just has a gradient of a half, right? So we can just use the reverse chain rule to anti-differentiate that. Okay. So here we go. Let's we've got our integrals. Let's find our primitive functions. Okay, I'm going to pull the constant pi out the front. Right, this is not. This is supposed to be 4. Okay, 0 to 4. Sorry. Okay, so we're going to pull the constant pi out. Right. Let's anti-differentiate. 4 minus x is going to give me 4x minus x squared over 2 from 0 to 4. And I want to take away, again, I'm going to pull the integral, or I'm going to pull pi out of the integral. We're going to get 2x, all right? Let's start that again. We need to use the reverse chain rule here, sorry. So we're going to get 2 minus x over 2. I'm going to raise the power by 1 to 3, divide by the new power, and I'm also going to divide by the coefficient in front of x. In this case, it's just negative a half. Okay, this is from 0 to 4. But we can tidy that leftmost one up, or the rightmost one up. So let's just get this as 4x minus x squared over 2 from 0 to 4. Take away, right, pi. Okay, this bottom denominator is going to become negative 3 over 2. The 2 will jump up to the top, so will become negative 2 minus x over 2 cubed, divide by 3. Okay, so there are my two integrals. Now I can evaluate them. So what I'm doing is I'm taking pi, and we can call our first function f. So f prime, okay, at 4, take away f prime 0, and I'm taking away pi. And if you want, just for, we can call this a different function. This can be g at 4, take away g at 0. Right? Again, it doesn't really matter what we call them. The important thing is you're stating that you understand what you're doing. Okay. So time to put the numbers in. So let's not forget pi here. We're going to be substituting 4 into our equation. So we're going to get 4 times 4, take away 4 squared, divide by 2. And you can see when I substitute in 0, I'm going to get 0, take away 0. So this will be minus 0. And this whole thing is being subtracted from the volume from the inner volume. So we have pi. I'm substituting in 4, so we're going to have minus 2 minus 4 over 2, all cubed and divided by 3. And I can see I'm going to be taking away, now this time we have to be careful, because even though we're taking away 0, that's not going to cause the whole thing to become 0, right? There's still going to be something left over. So we're going to get minus 2 minus 0 cubed all over 3. Right, the inside's going to give me, this is going to give me 16, and it's 16 divided by 2, so that's 8. So we're going to have pi 16 take away 8 over there. And this is all been taken away from pi, and I've still got quite a lot of stuff to deal with on the inside here. Okay, so we can deal with this one step at a time. We have 2 take away 2, which is going to become 0. So this portion here, right, is actually going to become 0. And this portion here, all right, we're going to have negative 2 right, multiplied by 2 to the power of 3, which is 8, right? And we have 8 times negative 2, which is going to be negative 16 divided by 3. So we're going to have negative 16 on 3. Okay. You can see that those are just going to cancel out and become positive. Okay. And so what we have here is pi, 8 pi, right, from the first integral, take away 16 pi over 3. And this is going to give us 8 take away 16 on 3. This is going to give us 8 pi over 3, and this is units cubed. Right, so that's the volume if we rotated that shaded area around the x-axis. Okay, part B asks us to now rotate the same shaded region, except this time instead of around the x-axis, we're going to rotate it around the y-axis. Okay, so the idea is exactly the same. The only difference is because we're rotating around the y-axis now, we need equations x equal to something. So let's manipulate both of our equations into x equal to something. Okay, so to get x out of here, we're going to square both sides. We're going to get y squared equal to 4 minus x. If I throw x on the other side and y on the other, if I swap them around, I will get x equal to 4 minus y squared. Okay. The other one's pretty easy as well. I'm just going to get x equal to 4 minus 2y. Right, I'm going to write the generic formula for the volume of something around, rotated around the y-axis, just so we have something. We can say C and D of pi. We need area, right? And when we are integrating around the y-axis, our radius, right, is just the x-coordinate, and it's pi r squared, so it's x squared. There's my area, and the width of all of these tiny little cylinders is just a little change in y. So a tiny little change in dy is what we're multiplying our height by. Okay, so to work out the volume of this this shape, right, we're going to imagine taking the volume underneath the whole curve, and then we're going to subtract the volume on the inside underneath the straight line, and that'll give us the volume of the shaded area if it was rotated around the x-axis. So let's define our integrals. Volume is equal to the integral from 0 to 2, and we have pi, right, r squared, or x squared in this case, is just that over there squared, so we have 4 minus y squared all squared with respect to y, and we're taking away the inner volume, okay, from 0 to 2, and this is pi. X squared in this case is going to be 4 minus 2y squared with respect to y. Okay. So the temptation to combine the two is there, but like I said, with volume questions, sometimes it's just better to deal with these separately. Right? I can see I'm integrating from 0 to something, so the integrals shouldn't be too difficult to work with in any case. So we have to have a look at this function here. Okay, this is not a linear function, and so it's not something that I can easily anti-differentiate. We haven't learned how to do that yet, so what we're going to need to do is expand that out so that we can actually find the primitive function. So that will be my next step, or in fact I can actually just do it underneath here, and we can look at it and evaluate the primitive. So I'm going to get 16 minus, this is going to be minus 4y squared times 2, so minus 8y squared, and I'm going to get plus y to the power 4. There's my x squared, right? On the other side, right, I do have a linear function, and I can just use the reverse chain rule to anti-differentiate. Right, I'm going to pull pi out because it's a constant. It doesn't matter, nothing's going to happen to it. let's anti-differentiate this now. All right, that's going to give me 16y divided by 1 minus 8y cubed over 3 plus y to the power 4, oh sorry, not 4, to the power 5 over 5 from 0 to 2, right? That's the volume of the solid underneath the curve, right? Now we want to take away the volume of the cone, right? So let's go take out pi again. Let's anti-differentiate this, so we just write the function down, right? So we're going to have 4 minus 2y, we're going to raise by 1, divide by the new power, and we're also going to divide by the coefficient in front of y this time, because that's what we're anti-differentiating this time, right, with respect to y, from 0 to 2. Okay, time for us to, sorry, we've still got some notes here, let's just delete those. Okay, time to evaluate my primitives, right? We want, I'll just for interest sake call this f, well, most importantly pi of f of 2 take away f of 0. Let's call that the curve function. Now we're going to take away pi, but this time let's call this guy g, just so we don't get confused. And let's see what we get. Okay, these two, just by the way, this just becomes minus 6, right? So a lot of number crunching to do, so just be careful. All right, fortunately that when we're evaluating from 0 to something, the zeros kind of help us out. So this we've got here is pi, right? And f of 2, right, is going to give me 16 times 2, take away 8 times 2 cubed over 3, plus 2 to the power of 5 over 5, okay? Take away, well, I can see if I put 0 into any one of those, I'm going to get 0, so I'm just going to say take away 0. That's my f function, that's my first integral. Now we're going to take away the second integral being the volume for the cone, which we want to remove from the inside. Take away pi, okay, and let's evaluate this. When I plug in 2, so I'm going to get 4 minus 2 times 2 cubed, right, all over negative 6. That's my f of 2, and I'm taking away 4 minus, well, 2 times 0 is going to be 0, all cubed, divide by minus 6. Okay, we're going to get pi. So what do we get here? Well, we can just work this out on the calculator. We get 32 minus 8 times 8 is 64, divide by 3, so minus 64 over 3, plus 2 to the power of 5 is 32, and that's divide by 5, right? So here we're going to get 256 over 15, take away 0 obviously, and we're going to subtract. Right, if we have a look at the first part of this, okay, the first part of this is going to disappear because this is 4 minus 4 cubed, which is just 0. So this first part becomes 0. Right, the second part is going to be 4 cubed divided by negative 6. So that's going to give me 0 minus, very important, when you get a negative answer, write it with the brackets, minus 32 over 3. Okay, so those are just going to cancel each other out. Okay. Okay, so this minus and minus will just become 32 over 3, and that makes sense because otherwise there would be no volume. It didn't exist, and that doesn't make sense. Okay, so the volume for the cone is 32 over 3, well, pi 32 over 3. Okay, so finally we can put everything together. We have, we can actually even write this as 256 pi over 15 take away 32 pi over 3. Right, this gives us, well, let's take 256 over 15, take away 32 over 3. This gives me 32 pi over 5, and this is volume, so it's units cubed, right? And if I have a look at the answer in the textbook, we get 32 over 5 pi. So there we go. We have an example of rotating around the y-axis and the x-axis, and when we have to deal with problems where we aren't dealing with volume all the way with bound by either the x or the y-axis, right, where we have the volume of a shaded area that is rotated, right? So it's very similar to area, right, except usually when we're doing area we can combine the two functions. We can subtract them away from each other when we're defining our integrals. With volume we can, except we have to be very cautious. So the best thing to do is just to separate the two integrals and evaluate them separately, right? It gives us the best chance of getting the correct answer, right? Hope that helps.